So, we will look at a method for determining the interaction between protein and ligand. This is based on what is called as translational diffusion. So, this is a very popular method in NMR spectroscopy, and this is known as diffusion ordered spectroscopy. So, we will see how that can be used for determining the interaction of a ligand, small molecule, with a larger molecule such as proteins. So, diffusion ordered spectroscopy is also known as DOSI. This is the acronym for the experiment, and this is a very useful experiment to determine the mobility of compounds. So, we are looking at now translational mobility. Remember, there are two types of mobility in molecules. One is known as a translational mobility, another is rotational mobility. Rotational mobility essentially is a rotational tumbling of the molecule, which is characterized by the rotational correlation time. So, that is something called tau c, which we have seen in earlier lectures when NOESY, especially when we discussed NOESY and ROSY. But here we will be looking at another type of diffusion, that is called translational diffusion. So, how the molecules move in space as a function of distance. Okay, so, this is an experiment which is useful for that, and typically DOSI is used for studying interaction of small molecules with proteins. So, this is a very popular technique used in drug discovery for screening a large number of molecules to see whether they bind to the target protein or not. And it is useful for identification of individual compounds in a mixture. So, suppose let us say your mixture has 2 or more molecules, you do not know whether there are number of molecules are 2 or 3 or so on. So, if they are different in size, then one can actually use DOSI to differentiate or separate the molecules, but the main thing is they should have a difference in the size, because translational diffusion, as we will see later, is very critically dependent on the size of the molecule. So, the higher the size, the bigger the size of a molecule, it will diffuse or it will move slowly in a solution. Similarly, if the molecule is small in size, it will diffuse faster in solvent. So, that is what basically the idea is, that diffusion is order spectroscopy tries to exploit the differences in the molecular diffusion based on their size. Now, therefore, if size becomes an important parameter, then one can also use this approach for studying aggregation of molecules. So, let us say your molecule is aggregating from a monomeric state to a dimeric state to a tetrameric state and so on, then one can use DOSI to study or track how the aggregation is going on, because as the aggregation proceeds, your molecular size will increase, and if the molecular size increases, your diffusion will slow down, and if the diffusion slows down, it can be captured by this experiment. So, these are basically a few reasons or main reasons why DOSI is very popularly used in NMR. So, we will go through this and look at how we can study interaction of ligand with protein using this technique. So, again look at this picture which we have seen earlier. So, suppose let us say you have a small molecule ligand, it is some kind of a drug which interacts with protein. So, you have this complex which is formed. Now, let us assume that the complex is strong, which means the ligand has a high affinity for the protein, which in other words implies that the protein is the ligand are tightly bound to the protein. So, in such a scenario, the ligand being a small molecule, the free ligand will have a high diffusional or higher diffusional rate in the unbound form, means in the free form. So, in the free form, the ligand will have a higher diffusional rate because it is now not bound to the protein, but upon binding to the protein, the ligand behaves like a large molecule, and therefore, its translational diffusion reduces. So, this is the main point here, is that we are trying to differentiate or take the difference between the ligand in the free form versus the ligand in the bound form. So, this is a point here which is mentioned here also, that based on the difference in the diffusion rates, the interaction of ligand with protein can be inferred. Okay. So, now if the ligand binding is not strong, then there will be another complication. So, there are two possibilities, or let us say three possibilities. Possibility number 1 is that the ligand does not bind to the protein at all. If that happens, then there should not be any change in the diffusion of the ligand, because it remains in the unbound form. Whether the protein is present or not, the diffusion of the ligand should not change if it is not binding to the protein. But imagine another scenario where it binds to the protein, but does not bind very tightly. A loose binding means a weak interaction. In a weak interaction case scenario, the protein now and the ligand remains in the free form as well as in the bound form. So, both these forms will exist in a dynamic exchange with respect to each other. Okay. So, this dynamic exchange therefore will cause an average diffusion of the ligand between the free form and the bound form. So, the diffusion what you will measure or observe in the spectroscopic technique will not be the free ligand diffusion rate, neither will it be the diffusion in the bound form. What you will observe in a loose binding situation, that the diffusion will be an average of these two states. Okay. So, that is the case with a weak binding scenario. And the third scenario is a tight binding, means it binds very tightly, and therefore, the population or the amount of free ligand in the solution will be very less. And so, if that is the scenario, then the ligand will diffuse like a protein, because it is now belonging to this bigger complex, and therefore, its diffusion will be considerably reduced, and it will diffuse like a protein size. So, in such scenario very easily we can now distinguish the bound form and the free form. So, let us see how this diffusion order spectroscopy helps to differentiate the two states by using the diffusion rates. So, before we go into the DOSY details, we have to first understand a basic concept in NMR which is required for DOSY. Okay. Now, this idea of using diffusion to decide whether the ligand is binding or not is known as affinity NMR. And a large number of ligands in the drug industry or pharmaceutical companies are screened in the initial stages by adding the ligands to the protein sample and then observing whether the translational diffusion has changed or not. Those molecules, when we add to the protein, those which show reduction in translational diffusion are then considered to be the binders or considered to be binding to the protein. So, this is the standard definition or approach in for a drug discovery process, and the word affinity NMR you will see being used in literature to determine whether diffusion can be used or not for binding of ligand to proteins. So, let us now move into how diffusion DOSY experiment works. For that you have to first understand a basic concept in NMR that is known as gradients, and this is something we have not covered in extensively in this course. So, I will give a very brief introduction to the gradients, and then we will go on to how gradients are used in DOSY. So, what are gradients? Gradients are coils. You can see these are like coils, circular coils, and these coils are present here. You see this is called as a NMR probe. This whole cylindrical thing here is an NMR probe, and the probe goes into the magnet. So, if you recall how the NMR system is spectrometer is built, NMR spectrometer consists of a magnet, it consists of console, console means the electronic components, it consists of a probe. A probe is basically where you put your sample. So, you see where this arrow is pointing right now, our sample typically sits there. So, there is this RF coil, you can see this observe coil and decoupling coil. These are these coils which are kept there, are there, and above and below this coils RF coil you will see these circular coils called gradients. So, what happens in a gradient is a current is supplied in this coil. So, a current flows in a direction like this in the coil. This coil is sitting there in the top position here, and in the down coil will go in the opposite direction, and that will be in the bottom of this RF coil. Okay. So, you see there are two opposite gradients, they supply current in the opposite direction and they will therefore cancel each other, but not always. We will see that how it gets cancelled, how it gets added up and so on. But these gradients, when you supply current in a coil, what happens? What happens is a magnetic field is generated perpendicular to this plane of this coil. So, suppose you imagine this plane as a xy plane. So, this is in the xy axis, xy direction. So, you can think of the ring of the coil like this. So, whenever you have a coil like this, a current is flown in this coil and this generates a magnetic field in the z axis. Okay. This is something very similar to what we do with the main magnetic field. The main magnetic field also consists of superconducting coils which can carry the current, and that generates a main magnetic field, and the gradients are also magnetic field, but the magnetic field they generate is very small. This magnetic field typically is of the order of Gauss. Okay. So, it is not a very big, remember 1 Gauss is 10 to the power minus 4 Tesla. So, we are generating a very weak magnetic field from the gradients. So, gradients generate an additional magnetic field on the sample. Okay. So, this is in addition to the external magnetic field which is already present. This is something we do not have to think about because this is the main magnetic field, but by turning a gradient, applying a current in this coil, okay, it generates a magnetic field. Now, suppose I apply a current in the opposite direction in this coil down, then the magnetic field will be in the opposite direction. Okay. So, this is called the right hand rule. Okay. So, one has to keep that in mind, that when you supply a current, it basically generates a magnetic field like this, and if you oppose the apply an opposite current, it will basically go to this opposite direction. Okay. So, basically you have to look at clockwise versus anti-clockwise. So, we can think of it this as this direction also and this as this direction. Okay. So, any direction you apply, it will generate a magnetic field corresponding to the right hand rule, and the other coil which is here will be opposite in this direction. So, now let us see what is the effect of this on the sample. What happens when you apply a gradient current in a coil like this, and what happens when into the sample. Now, one thing is this gradient coils are nowadays standard in all NMR spectrometers, but olden days 20-30 years ago, these gradient coils were not there in the probe. So, now second point is that this gradient is along z axis. Why it is along z axis, we will see that shortly, but you can also apply gradients in the xy direction. So, if I turn this coil around, if I keep the coil like this, then the gradient will be like this in this direction. So, it depends on what direction you put, the gradient will be depending on that. So, in our case, in a standard NMR spectrometer, routinely, typically, you will see that these gradient coils are situated like this in the xy plane. So, that magnetic field which is generated is in the z axis, that is Gz. Okay. So, this Gz is known as a gradient. We will see this gradient how it looks shortly, but keep in mind again, we have a small coils in the probe where we apply current in opposite directions, and that generates magnetic field, additional magnetic field. Now, let us see what is the effect of this additional magnetic field on the sample. So, now look at this picture here. So, let us say this blue color, what you see in the blue is our sample kept in the sample tube. So, sample tube is this rectangular portion shown here, okay, this full rectangle, out of which let us say we have filled the sample like this. Now, the effective sample volume, meaning the RF coil is somewhere between these two coils. It is not shown here, you can think of this dotted line also as a RF coil, but this, remember, if you go back to this picture here, what you can see here is that this gradient coil are sitting at the ends of the RF coil. So, RF coil is like this, the gradient coils on top and bottom of the RF coil. So, this is what is shown here. You can think of this middle portion as the RF coil, and the top and the bottom is basically your gradient coils. Now, this what is shown in this dotted box, or the one which basically is covered by the RF coil, is our effective sample volume. What does this mean? It means that whatever NMR experiments you do, your experiment is basically, your sample is what is generating the signal is coming only from this portion. The portion below and the portion anything above is no use. Why? Because it is not seen by the RF coil. So, RF coil and the gradient, I mean this portion essentially are the main part of the sample. Sample is molecules in the sample in this portion are the ones which are finally giving you the NMR signal. So, this typically is about 250 to 300 microliters in a 5 mm tube. Suppose your tube is 5 mm in diameter and you have a 5 mm probe, then your actual volume of the sample which is effectively seen by the probe is about 300 microliters, whereas you take about 600 microliters in your NMR tube. So, half the sample is essentially not visible to the NMR spectrometer or to the coil, but that is not the important point here. The point here is that this effective volume is essentially the volume which is seen by the RF coil and the gradients. So, now so imagine, so this is what is shown here in this picture on the right hand side. You have this effective volume, this blue color shaded portion. So, now imagine that there is a molecule at the top of the sample, and imagine the same molecule another copy of it in the bottom. So, remember our sample contains a large number of molecules. So, if you take for example 1 millimolar sample, you have a huge number of molecules, 10 to the power almost 20. So, when you have such large number of molecules, obviously you have them distributed throughout the sample. They are not sitting in one side of the sample, they are spread throughout the sample, because we are assuming it is a homogeneously soluble sample. So, if you imagine a molecule which is at the top part of the sample and at the bottom part another molecule, you see these two molecules. Now, when I apply the gradient, means I apply this RF current in this RF coil here and here, okay, what will happen is the following. The molecule at the top will experience an additional magnetic field in addition to B0. Now, what is that additional magnetic field? The additional magnetic field is given like this. It is based on the strength of the gradient, means how strong is the current in the gradient coil or how strong is the magnetic field generated, multiplied by the Z. Z means its distance from the center. Okay. So, imagine if this is your center, this part is this Z. Okay. So, center is now considered as 0 and this is B minus Z. So, Z is basically just the distance of the molecule from the center of the sample. Okay. So, what happens is when I apply a gradient, I am applying two opposite magnetic field. Okay. So, the magnetic field and this coil, remember I showed in the last slide, is in the upward direction, and the magnetic field and the lower coil is in the downward direction. So, therefore, a molecule which is at the bottom of the sample experiences an opposite magnetic field compared to the molecule at the top of the sample. Okay. So, this additional magnetic field are in addition to B0, which is our external magnetic field which is already present. So, remember B0 is always present, we are not disturbing or we are not changing that value. What we are doing is we are creating or we are adding an extra magnetic field at the across the sample, wherein the topmost part gets this addition magnetic field and the bottommost part gets a subtracted magnetic field. What happens in between? In between there is a range of G value, because the z will change, right. So, for example, if you take here z equal to 0, so the magnetic field is just B 0, there is no addition to the external magnetic field because z is 0. So, when you put z equal to 0 here, this becomes 0. So, total magnetic field now for this molecule, suppose I have a molecule sitting here, then that will experience a 0 additional magnetic field. This is not 0, remember. Okay. So, what have we done here? What we have done here is that across the sample from the lower part to the top part, we have created a difference in the magnetic field, and that difference is a linear. You can see this is a straight line, it is a linear, it goes from minus Gz to plus Gz linearly. Okay. So, this is a very important thing, we have deliberately, means purposely we have created this difference in the magnetic field. If the G value was 0, then you can see that there will not be any gradient. So, when is G equal to 0? G is going to be 0 when there is no current in the coil. So, when I do not apply any current in the gradient coil here and here, it means my G value is 0, but if I apply a current, my G value will be some value. Now, I can change the current strength. Strength means how strong the current is. I can go from very low strength to very high strength, or I can keep it for a longer duration. I can apply a current of some value and keep it on for a long time. But what is the time typically we keep it on? The gradients are very short durations. We typically keep it on for a few milliseconds. Okay, so, microseconds to milliseconds. So, therefore, it is like a pulse. So, gradient is also like an RF pulse which is applied for a very short duration. The current in this coil is applied for a short duration, not for a very long duration, but in that time whatever has to happen, we will see now what goes on. But the G value is another thing. G value is the strength of the current, how strong is your current in the coil, and that will decide how strong is your additional magnetic field. But another parameter is the time, that how long do you apply the gradient, and that does not affect the magnetic field, it only affects some other parameter, but it will basically tell you how long the magnetic field is present. But as I mentioned, it is typically of the order of a few milliseconds. So, therefore, the gradients are very short in duration, and you can think of it as a pulse. Okay. So, now let us see what happens when you apply this gradient to this sample. So, let us say I have a 1D pulse, I have applied a pulse, an RF pulse. So, this is an RF pulse. Okay. Now, this is for proton. Now, suppose after the RF pulse I apply a gradient. So, gradients is typically we show like this, we call it PFG. This is called pulsed field gradient. PFG is pulse field gradient, and this gradient, let us say we apply after the RF pulse. So, when you apply the 90 degree RF pulse, the magnetization is in the XY plane. Okay. So, now I apply this gradient. So, what will happen? The magnetization now is precessing, going to precess with the without the gradient. Suppose gradient is not there. If the gradient is not there, this will precess with omega naught equal to gamma into B 0. This is the standard NMR formula which all of us know. But when you apply a gradient, so when I apply a gradient now, what will happen is the molecules which is on this side of the sample and molecules which are on this side of the sample, they will not have the same omega value, because if you look at this equation here, the omega 0 or omega of this molecule has changed, because now the total magnetic field experienced by that molecule is not B 0, it is B 0 plus G into Z, where Z is the distance from the center. Now, if you look at the same molecule, but now there is a copy, means there is another molecule of the same type which is sitting at the bottom of the sample, it will have a different Larmor precession. Its precessional frequency has changed, it is now B 0 minus G into Z. So, now what is happening is the same two molecules, the same proton in a given molecule. For example, you take ethanol, any molecule, the particular hydrogen in that molecule, if you are looking at that, the same hydrogen, because it has a copy on the top of the sample, along the sample and bottom, each part of the sample, that is proton, experiences a different omega value, because at every point in this sample you see here the omega is not the same, omega is changed because of this additional factor. So, because of this you see all this omega, the different omegas, so they start going in different speed, they start dephasing now because of the difference in omega 0, and this difference is around across the sample. So, therefore, when you combine the signals, all of these signals are finally going to the receiver. Okay. But now the receiver is not going to get a single signal, it is going to get a signal which is completely dephased, because each molecule in the sample is having a different omega value, omega naught value, precision, normal precision value. So, because of this complete change or spread of the omega value across the sample, there is a complete dephasing of the system, because each velocity, this can think of this arrow shown as a velocity or speed, the speed all changes, the oscillation frequency changes for every sample here, every molecule here in the same sample and the same proton, but located at different region of the sample. So, therefore, when I combine all of this to get a single signal, because remember receiver does not know where the signal is coming from, the receiver takes the signal from the entire sample. So, the receiver now gets a 0 signal, because the complete signal you see is all dephased and it has become gone to 0. So, any signal here is cancelled by a signal here, any signal here is going to be cancelled by signal here, and so on. So, this is why a gradient completely kills the signal. A gradient is a very simple approach to simply destroy or remove or suppress any signal you want, and this suppression or dephasing, you must keep in mind, it is not due to T2 relaxation, because T2 relaxation also causes dephasing, but the T2 relaxation is a slow process, it takes 100 milliseconds, 200 milliseconds, whereas by applying gradient which is only 1 millisecond, we can achieve this complete dephasing. So, gradient therefore is a very fast way to remove any signal from your sample or destroy the or suppress the signal.